How do we use SLURM to launch an MPI program? MPI jobs run on one or more nodes. They get speed up by running parallel processes on different CPU cores. These processes can communicate by sending and receiving messages across the cluster's network. For example, each of Faster's 180 compute nodes has two 32-core Intel CPUs. So an MPI job can have up to 180 nodes times 64 cores per node equals 11,520 processes. The number you should specify depends on the program you're running. Since we're already connected to Texas A&M's Faster cluster, I can use the cd command to change my location within the directory structure to that MPI folder. Being in the folder, I can view its contents using the ls command. This reveals the files 2x8-script.slurm, makefile, and mpi-hello.c. The source file mpi-hello.c is a simple MPI program that has each process output a greeting that includes its process ID, the number of processes, and the name of the node on which the program is running. Before we can run the program, we must build it from its source file. Unix family systems provide a utility named make to simplify this task. The details of using make are beyond the scope of this demo, but the file named makefile coordinates the build. So with a makefile in the project folder, I can in theory build my program by just entering make. But when I do so, I get an error. Studying the output, this makefile tries to build my program using the MPI-CC compiler. It does not find it, and so generates a command not found error. I contacted the Faster help desk team. They told me MPI-CC is stored in the FOSS/2023B module, and that I can load that module by entering module load FOSS/2023B. Note that if the makefile was using Intel's MPI-ICX compiler, I would have instead loaded the Intel/2023B module. With the required module loaded, I now rerun make. And now my program builds without any errors or warnings. If I enter ls again, I see that there's now a new file named mpi-hello in my folder, shown in green. This is my runnable program. To run our program on Faster's compute nodes, we use the file 2x8-script.slurm, which is a SLURM job request script. You can have multiple SLURM scripts in the same folder. I like to code the number of nodes and processes into the script's name, but you can choose any name. We can view the contents of this script using the cat command. Inside, we see the shebang line, followed by a bunch of SBatch options. The first option is the job name. I can choose any name I wish for that. I like to choose the program name. This is an MPI program, so I'm requesting 2 nodes. To limit its output to 1 screen's worth, I'm requesting 8 tasks or processes per node. Since this is an MPI job, I specify 1 core or SLURM CPU per task. I specify a minimal amount of memory, then tell SLURM to stow our output from the program in a file named slurm dash, followed by the job number, followed by .out. You can name this file anything you want, but specifying the %J job number will give this file a unique name. We then tell it to use SLURM's CPU partition, and then specify 5 seconds as its maximum runtime. This is a short program, so even 5 seconds is overkill. Since we're requesting multiple nodes, it may take SLURM a while to schedule this program, so I have enabled these email notification lines. You may also specify the account to be charged. Some RPs require you to do this, but Faster will charge your login account by default. Since our program used the free open source MPI libraries when we built it, we must tell SLURM to load that same module before we run the program. And last, we tell SLURM how to run our program. For MPI programs, you can do this using the MPI run command, followed by the name of the program. The / tells SLURM to find our program in the current directory. You can also specify any command line arguments your program requires here. Our simple program doesn't need any. With our SLURM script complete, we can ask SLURM to run our program using the sbatch command. Sbatch followed by the name of the script file. SLURM responds with output that includes a job number. If I highlight that and copy it, I can check the status of my request using the sq command, followed by -j, followed by the job number. I get a bunch of column headings with no output following them, and so this in fact means that my program is already finished. If I do an ls, I see a new file, slurm-2575258.out. If I cat that file, I see the output from my program. Greetings from process number whatever out of 16. One thing to note is that half of these are running on one of Faster's compute nodes. The other half are running on a different Faster compute node. Since Faster has 180 nodes and 64 cores per node, this same program can use more than 2 nodes and up to 64 processes per node. For example, if I wanted to run my program with 4 nodes, using all 64 cores on each node, I could use the cp command to copy my existing script. I can then use an editor to adjust the necessary values in the new script. When I'm done, I save my changes and then use the sbatch command to submit this new script. This may take a while, so once again I can copy my job request number, use sq-j to check the status. Now I see that my program is now listed as pending until the resources, it's waiting basically for the resources it needs, 4 nodes, 64 cores per node, to become available. If I had multiple job requests pending, I could do sq-u space and then copy my username, paste that, and this would give me a list of all of my pending requests. But rather than waste time on Faster, let's cancel this job. I can do that with scancel, followed by the job number. And now if I repeat the preceding command, I see that my job is no longer in the queue, so it has been successfully canceled. That concludes this demonstration of SLURM and MPI. I encourage you to watch the final presentation in this playlist where we summarize what we've done.